Welcome to your wave review video. I'm going to be going through this packet here and jumping around, showing you some different things on the computer here. First things first, here's our wave. This is our normal transverse wave, which we saw in our FET here. And the direction of the wave is side to side, right? But the direction of oscillation is up and down. And that's kind of what this question asked right here is, what's the direction of the wave moving? The wave is moving left and right, but the particles, if you watch this green dot, are oscillating up and down. So let's go through some of the other parts of the wave. We've got the trough and the crest. We've got the wavelength, which we can measure from crest to crest or from trough to trough. And we've got the amplitude, which you measure from the middle of the wave to the upper part. And don't ask me why it's not all the way down here. I don't actually know. So those are the crucial parts of the wave. You definitely have to know that. So when we're making waves in the long spring, what wave property can be directly changed? Now I bolded the wave properties up here, but really these four are the main wave properties. Medium is maybe a wave property. It's kind of interesting. Medium means what a wave is traveling through. So the medium it decides a lot of things about the wave, but it's not really a part of the wave. It's very, very kind of medium. But when I ask for a wave property, medium is a possibility on this review. But in this case, we're directly changing, in the long spring, we're changing the frequency, right? We're directly changing it. When you spin faster, we can change the frequency of the wave. Now what changes as a result? You might have just seen it. Here's a high frequency, here's a low frequency. We can see that we've got different wavelengths, right? With a high frequency, they get really close together. With a low frequency, it gets much further apart. The wavelength gets much bigger. So, what wave changes as a result of our change? Wavelength. In this case, it was frequency. So what three properties stay the same when the frequency changes? Well, again, let's look at our wave on a string. The amplitude is its own bar, so that can't change. The tension didn't change because of the frequency, so that didn't change. And then there's the other thing that we did together, which was the wave speed. And we found that the wave speed does not change if we change the frequency. Let's count it off. 1 Mississippi, 2 Mississippi, 3 Mississippi, 4 Mississippi, 5 Mississippi to go 5 centimeters. And if I take the frequency way down, it's still 1 Mississippi, 2 Mississippi, 3 Mississippi, 4 Mississippi, 5 Mississippi. Now that wave is much bigger, but the speed is the same. So our three properties that stay the same when the frequency changes are the wave speed, the amplitude, and the medium, which again is kind of a wave property. It doesn't change when we change the frequency though. So let's look at each of these relationships between these variables. Frequency affects the wavelength, but doesn't affect any of the other ones, medium or wave speed. Wavelength doesn't really affect them. It's kind of the result. It's the result of, by changing the frequency, we can change the wavelength. By changing the tension, we can change the wavelength, but we can't directly change the wavelength. The medium affects the wave speed, which would in turn change the wavelength, but you don't need to know that necessarily. Just the idea that medium affects wave speed is what's really, really important here. Wave speed is like wavelength, though. It's the result of the other variables. You can't change it without changing the medium. Frequency does not affect the medium or the wave speed. So why can't sound travel in space? It's simple physics words, no medium. Compression waves require a medium. Now, compression waves. That's not something we've talked about too much. But this wave that's particles oscillate in the same direction as the motion of the overall wave is called a compression wave. This is a GIF of a compression wave, where the particles, you can see a couple of them in red, are moving in the same direction as the wave itself. This is how sound waves work. This little gray part would be like the vibration of my vocal cords. And they would hit the air next to that, which would hit the air next to that. And the old particles kind of stop and bounce back as the compression wave moves forward. And so we can see that a wavelength of a compression wave is measured from like thick area to thick area. You can see each time this pushes a bunch of particles, but the particles do not move all the way to the other end. The particles oscillate back and forth, and the wave goes side to side also. That makes this a compression wave. So waves, its particles oscillate in the same direction as the motion of the overall wave, which is called a compression wave. Then the opposite, our other kind, which you could also have written right here, is these waves where the particle oscillation is in a different direction than the overall wave movement. So this would be a transverse wave. We've talked about this one a little. Wave speed is determined by the, what is it? That tension in the string, the medium of the wave, what the wave is traveling through. So that frequency can't affect it, the wavelength can't affect it, only the medium can affect the speed of a wave. So when a wave fits perfectly in its medium by half wavelengths, we call that, that's what we got in our little demonstration in the back, we got a nice standing wave. And so here's a good little GIF of a standing wave. And these red and blue are showing the reflected wave that's coming back on itself. Notice how at the nodes, those things are lining up at the nodes, but at the crest and trough, the two are adding together. Let's watch this red one coming over here. It meets the blue one right there, and that's when we have that constructive interference. Here's another example of it. We've got lots of different frequencies going on here, and it's not fitting at first. This is not a standing wave. Until you find the right frequency, and that makes the right wavelength, then you get a nice standing wave. And so they're dialing it and changing it, and so then they finally get a standing wave going. And so this is the third harmonic. This is 1.5 wavelengths. But the other frequencies are not making that same standing wave. Only certain frequencies make the standing wave. So when a wave fits perfectly in medium, a standing wave occurs, and we call that frequency the resonant frequency of the medium.